This is an example script written in the language we are going to implement. As you can see, we can define some functions with parameters. They can return values, define variables, and assign integer, boolean, and string values to them. It's possible to conditionally execute code and have loops. Anything else is achieved by invoking functions on objects, possibly passing other objects as arguments. You may notice a special variable, interpreter. This variable is used to invoke user-defined functions. It's not possible to define types in the language for simplicity. They can only be defined by the host language. To start, we read this file into a string and then print it to the console. The first phase of interpreting a language is lexing. Lexing is the process of converting a string into a list of tokens. We do this because it's easier to work with tokens than with raw characters. Here are all tokens with corresponding examples in the code. You can see special symbols, keywords, literals, and identifiers. The lexer class takes the input string as a constructor parameter and stores the current position in it. Its single public method lex returns a list of tokens. It calls next token in a loop until the end of the input string is reached. The next token method first skips all whitespace characters, moving the current position to the first non-whitespace character. Then it checks the current character and based on that decides which token to return. If the current character is a letter, it reads all consecutive letters and digits to form a string. If the resulting string matches a keyword, it returns matching keyword token, otherwise it returns an identifier token. If the character is a digit, it reads all consecutive digits to form an integer token. If it's a double quote, it reads all characters until the next double quote to form a string literal. Lastly, it tries to match single character tokens. If no match is found, it throws an error. Here is how we can use the lexer. Let's also quickly define a function that converts a token to its string representation and print the list of tokens using it. The next phase is parsing. Parsing is the process of converting a list of tokens into an abstract syntax tree, or AST for short. It's a tree representation of our code structure. Each node in the tree represents a construct in the language. The reason we build a tree rather than interpreting the tokens directly is that a tree naturally captures nesting. An if statement contains its body, a function call contains its arguments. Again, let's start by defining the data types of the objects we're about to produce. Here you can see the AST node interface and different classes for different constructs in the language. These classes are grouped into three categories: statements, expressions, and declarations. A statement is a construct that performs an action. Expressions are constructs that can be evaluated to a value. Declarations are limited to only functions in our language because we don't have classes or top-level variable declarations. This grouping is useful because it lets us express what is stored in AST nodes more precisely. For example, a function declaration stores its body as a list of statements, while an if statement stores its condition as an expression. And note that any expression will work here, making it possible to use function invocations as conditions, as well as variable references. There are two interesting node types. Program is not one of the three categories. It's needed to represent the whole program, which is a list of declarations in our case. Expression statement is a statement that simply wraps an expression. It's needed because function invocations can cause side effects, and we want to be able to use them as statements. The parser class takes the list of tokens as a constructor parameter and stores the current position. There are methods for parsing each construct in the language. Each such method assumes the current position is at the beginning of that construct. The single public method parse returns a root AST node representing the whole program. It calls parse declaration in a loop until the end of the token list is reached. From this point on, we will use a helper function that expects the current token to be of a certain type, consuming and returning it if so, and throwing an error otherwise. Because the only type of declaration in our language is a function declaration, parse declaration first consumes the function keyword, then expects an identifier token for the function name and an open parenthesis token, and then reads all parameter names, if any, until it finds a closing parenthesis token. After that, it parses the function body in a similar fashion to the main parse method. Let's now see what statements parsing looks like. It switches on the current token type. For if and while statements, it consumes the keyword, the condition expression, and the body. For return, it consumes the keyword and the expression. When the parser sees an identifier token followed by an equal sign, it parses an assignment statement. Otherwise, it falls back to an expression statement. Expression parsing starts with the primary expression, a simple one-token expression like a literal or an identifier. Then it tries to parse a chain of function invocations for as long as it finds dots. Each invocation consumes the function name and its arguments, recursing into the same parse expression method. Notice why invocation chaining works. The function call AST_node stores the callee as an expression, so the previously parsed expressions is passed as the callee for the next invocation. Again, we define a helper function that converts an AST_node to a string representation. And finally, we print the root AST_node of our program. The last phase is interpreting. We will interpret the AST directly by recursively traversing it. There are more sophisticated approaches, compiling to bytecode for instance, but direct tree walking is the simplest way to get something running and it's easy to understand. As before, let's start by defining some helper classes. First, a handle interface that represents any object available in our language. It has a single method call, which takes the name of the function being called and the list of arguments and returns a result. The arguments and the return value are handles themselves. The first handle type is a special void handle which has no functions available. Next is Boolean handle. It switches on the function name, unwraps the needed arguments, performs the operation, and wraps the result back. Int handle and string handle follow the same pattern. And finally, console handle. It's a little bit special because it calls the toString function on its arguments, which we already defined. The next important helper class is memory. It's essentially a linked list of hash maps. The get method first tries to find the value in its own map, and if that fails, it delegates to the parent. This structure allows us to easily support variable isolation between function invocations by deriving a new memory for each of them. Finally, the interpreter itself. It also implements the handle interface, because that is what lets the script access user-defined functions through the interpreter variable. The language calls the interpreter the same way it calls any other object. On initialization, it builds a map of defined functions to make the lookup easier and sets up the memory root, to which it adds itself under the name interpreter. The call function from the handle interface simply finds the needed function in the map and interprets it. Interpreting a function starts by deriving memory and pushing the passed arguments into it. Then it interprets the list of statements. Notice the control flow sealed interface. Without it, a return statement deep inside nested if or while would have no way to unwind back to the function boundary. Control flow is the signal that travels up through every interpretation call until the interpret function method catches it. Statements are interpreted sequentially. If any statement signals a return, the rest are skipped immediately. Statement interpretation is straightforward. Switch on the type and evaluate the needed expressions. If and while statements also interpret their body blocks depending on the condition evaluation. Return statements wrap the expression result and propagate it up. Assignments store the result in the memory by name. Expression statements simply run the provided expression and always return normal control flow. Expression interpretation also switches on type. Literals return the corresponding handles. Variable references look up the value in the memory. Function calls are a little more interesting. First, the callee expression is interpreted, then the arguments, and finally the call method of the callee is invoked with the function name and the provided arguments. We can finally instantiate our interpreter with already parsed AST and call the main function of our example script, remembering to pass console handle as an argument, and see the beautiful result in the console. If you've watched this video all the way through, you're probably already interested enough in interpreters to try building one yourself. I hope this video helped you build at least a high-level understanding of how a simple interpreting can be put together, enough to start playing around with it. Also, the language from this video is a subset of a bigger language I've been developing as a hobby project called PrimitiveScript. The GitHub repo link is in the description.